if ice did not do this? Eventually, most of the oceans of the world would freeze up. Someplace like Lake Tahoe. It would be frozen solid all the way to the bottom. And in the summer, a little bit of ice would melt on the top, and in the winter it would freeze solid again. What would happen to all the fish in Lake Tahoe? They'd be dead. They couldn't live there. Now, does that mean all the oceans would freeze solid? No, because you go to the temperate zones, obviously the things. But basically, anywhere where it freezes in the winter, eventually all water would fill up with ice. You know, so it would do a lot on that. It doesn't do that. Fish can live underwater in the winter. Fish produce like this natural antifreeze. You know, they get sluggish, but they don't die. But what happens? Notice, above 4 degrees Celsius, water acts like any other substance. You add energy to it, it's going to expand. You remove energy from it, it's going to contract. But at 4 degrees Celsius, that's the magic number. Remember we talked about that when we put together, we talked about the metric system. It's water at 4 degrees C is densest. Water gets most dense because when it's here, it's all liquid. 4 degrees Celsius is the lowest temperature water will have where it's completely liquid. Matt? Yes, ma'am. Morning, sunshine. So, water. So something happens to water when it starts. Notice I am continuing taking energy away, but it's expanding. It's expanding. So, it has to do with water crystals forming. At 4 degrees, as I remove energy from water, liquid water, after 4 degrees, ice crystals are starting to form. In other words, solid ice is starting to form. We cannot see it. We cannot see it, but these crystals are starting to form. Now, in most substances, the solid crystal, when it becomes a solid, the molecules will get closer. But water, notice how far the water molecules are as a liquid. When they become a solid, they get farther apart. And when they get farther apart, they get less dense. Less dense. This is why water floats, because that unique property of water crystals, solid water, that it gets farther apart, it will float. So this is that unique property of water. Because even if you looked up here at the periodic table, if you looked at hydrogen sulfide, H2S. Now usually you go down the chart, like if you went hydrogen fluoride, hydrogen chloride, hydrogen bromide, they're all acids. Do they have very similar properties? Yeah, they do. Sodium chloride, you look at sodium chloride, potassium chloride, rubidium chloride, lithium chloride. They would have similar properties. But hydrogen, basically dihydrogen oxide, dihydrogen sulfide, very different properties. Water, very, very different. These unique properties, along with enormous amounts of heat, floats. Floats. Nothing else does that. Well, what does that do for us? Well, let's take a lake. Now, if a lake is very deep and in a temperate climate, meaning it gets to freezing, the bottom of that lake is always going to be at 4 degrees. If you went to Lake Tahoe, the bottom of Lake Tahoe is at 4 degrees. It's always at 4 degrees.
4 or 40?
4. 4 degrees. 4 degrees. That's 4 degrees Celsius. 4 degrees Celsius. It's always at 4 degrees. You go to Crater Lake, it's 4 degrees. Man, those Crater Lake, Lake Tahoe, they're over 1,000 feet deep. Lake Tahoe is over 1,000 feet deep. What about Crystal Springs Reservoir? What's bomb temperature there? 4 degrees?
Yeah. No.
No. Now, actually, this time of year, Yeah, probably the bottom go to the very bottom, it's going to be 4 degrees because has it, like last few days, has it gotten below freezing? Last week it was getting below freezing at night, so there was water that was probably getting below 4. So right now there probably is water below 4 degrees. But do you think it's going to be 4 degrees in the summer? Probably not, because it has enough turnover that it actually will not be. Shallow lakes, you're not going to see this. We're talking about deep lakes. Deep lakes. Go to a lake in Florida, is it going to be 4 degrees in the bottom? No. So on that. So we have our water. Now at the surface, even Lake Tahoe, say it gets up to 10 degrees in the summer. So by the end of summer, the surface temperature is up to, say, 10 degrees. It's now fall. The temperature goes down, and the air temperature above is like minus 10. All right? Now, water is a bad conductor. Water is a very bad conductor. Heat. So, but the surface temperature is going to lose energy to the surface. It is going to lose it. So, it's going to go 9, 8, 7, 6, 5, 4. It gets to 4. What's going to happen to the surface water? It's going to sink to the bottom. And then another little bit of 10-degree water is going to come to the surface. Now, eventually, the whole lake is going to get to 4 degrees. All the lake is 4 degrees. It is only at this point can the temperature of the lake get below 4 degrees. In order for any body of water to freeze, all of it must first go to 4 degrees. Fresh water. Remember, we're talking fresh water here. Ocean water, we'd have to get colder, because remember, ocean water has to get colder. But the same idea. Now, at this point, it can get to 3 degrees. Now, the water right below it is 4 degrees. Is that 3-degree water going to sink to the bottom? No, because it's less dense. Remember, it's starting to expand again. 2, 1, 0, and all of a sudden it's going to freeze. And we get that. And as the winter goes on, that layer of ice is going to get thicker and thicker and thicker. Notice, basically, the temperature of the ice on the top is going to be whatever the air temperature is. Temperature of the ice on the bottom is going to be 0 degrees, because that's the temperature of the water right below. They're going to be at the same point. Bottom's still at 4. Our fish is still happy because it can swim around. And it will get thicker and thicker, and there are places in the country you can drive a car on the ice and things like that. And wouldn't recommend Lake Tahoe, because does Lake Tahoe freeze over completely? No. So what does that tell us? Does the lake ever all get to 4 degrees? No, but the shallow areas do. Shallow areas get cold enough that they can get frozen and things like that. Takes a lot. I mean, even Chesapeake Bay, the whole time I was at the academy, and it would get cold. The only time I only saw it freeze over one time. They had to call it the icebreakers. They froze over. The river would freeze over. Our river would actually freeze over, and but it wouldn't get very thick. We actually had a rule you weren't allowed to get on the ice of the river. Probably means somebody fell through it one time. But that's expansion and contraction. Questions? Which leads us to heat transfer. Heat transfer. Now, last chapter we talked about heat going from one place to another. Heat from one place to another. Glad I have a little exercise that gets you all out of your seats. Heat goes from one object to another with 3 methods: conduction, convection, and radiation. Now, we talk about heat is. Now, heat is that energy that goes from one object to another object because of difference in temperature. But there are three ways that happens: conduction, convection, and radiation. Anyone need a little more time? Stop tapping. So, conduction. Conduction. Transfer by direct contact. Things have to be in direct contact. Either you're touching something else, like when you touch the tabletop, you are losing energy to the table by conduction. This is how energy goes through solids. When you have that spoon in the water, that's how the energy gets through the spoon, that metal spoon. And this is what our lab is going to be about next class. It's about rate of conduction. And the rate of conduction, one, depends on the material. Obviously, some materials will conduct better than other materials. It depends on thickness. Think about a pipe. If I wanted to put a lot of water, bring a lot of water someplace, am I going to have a little skinny pipe or a real fat pipe to get a lot of water? I'm going to have a big fat pipe. Same idea with conductors. If I have a little skinny conductor, it's not going to carry much energy as a big fat conductor. Length, how far? The longer it is, the less energy is going to get there because we're going to lose some along the way. You're especially going to see that in our lab. You can feel it, that the bar gets very hot. Also, the difference in temperature. The greater the difference in temperature between the two ends, the greater the rate of conduction. It's like our walls. We lose energy through the walls of the room. Do we lose more energy during the winter or the summer? During winter, because there's a greater temperature difference between the inside and the outside in the winter than there is in the summer. So there's a greater rate of energy flow through the walls. Anyone need more time? So conductors and insulators. Now conductors transfer the energy easily. Now visualize. I have this big long line of soccer balls. I have this line of soccer balls all the way to the back of the room, and each soccer ball is connected to another soccer ball by a spring. If I grab my soccer ball and I start to shake it back and forth, it's connected by a spring to the next soccer ball. What's going to happen to that next soccer ball? It's going to start shaking. And what's it going to do to the next soccer ball? Make it shake. And eventually, is all that shaking going to get to the end? Yes, that's a conductor. It's going to get to the end. It's like putting that metal spoon in the boiling pot. If you leave it in the boiling pot too long and then you grab the handle, what happens? It gets hot. Ouch. It's going to hurt. Weak bonds, free electrons. By the way, this is the same reason they're good. We have good electrical conductors. Metals. Metals, we're talking here. We're talking pretty much metals. Pretty much all the things that are good conductors of electricity are good conductors of heat are also good conductors of electricity with a couple of exceptions. Like salt water. Salt water conducts electricity, it does not conduct heat. Insulators, though, they transfer thermal energy poorly. Not that they don't transfer it, but they transfer it poorly. They are going to delay the transfer. Now, we still have our soccer balls, but instead of having springs connecting them, they're connected by rigid iron bars. So if I shake the first one, is some of that shaking going to go to the second one? A little bit. And a little bit more, but eventually, am I going to transfer it all the way to the end? No, it's going to stop. That would be my insulator. It's like if I put a wooden spoon in, is the heat going to get up to the top? No. But if I pull that spoon out and grab the part that was in the water, is it hot? Yeah, the insulator is still going to get hot. It's going to store an enormous amount of energy. Those atoms that were in direct contact with the water are still going very fast. This is what happens during convection. We'll get to that, but that's why convection. But insulators and conductors. But we're going to do a little exercise here. Everybody needs to get up. Convection. All right. Now, convection is the transport of heat by mass movement of a fluid. Fluids are liquids and gases. And fluids are bad conductors.